everyone, and thanks for joining today's video. So today I'm going to be discussing a open source tool for retrosynthetic planning known as SynPlanner, and it's designed to increase flexibility in training and developing customized retrosynthetic planning solutions from raw chemical data. And it integrates a Monte Carlo tree search algorithm with graph neural networks to evaluate applicable reaction rules, known as a policy network, and synthesizability of intermediate products, known as the value network. SynPlanner can be used directly with pre-trained policy networks or fine-tuned on custom data through an automated end-to-end training pipeline. And additionally, SynPlanner enables the training of custom value functions on discovered synthesis routes to improve predictive performance. So what is SynPlanner? Essentially, it's an all-in-one Python package that includes workflows for reaction standardization, filtering, template extraction, neural network training, and retrosynthetic planning. So to begin with the Colab notebook, you'll begin by downloading the SynPlanner code from the GitHub repository, and you'll just install that via git using the first cell. Then in the second cell, you'll just define the input and output data locations. If you wanted to, you could mount your Google Drive here and you could set the output to your Google Drive so that your results will be backed up there. Then we'll load the building blocks, which are a collection that's built from the E molecules and sigma Aldrich building block datasets distributed through ASCOS and then standardized by SynPlanner. And then in the following cell, we'll load in the reaction rules, which are extracted from the USPTO reaction dataset using SynPlanner's own rule extraction pipeline, which features CGR-based reaction center extraction with tunable radius and ring/functional group inclusion, etc., etc. And of course, remember, SynPlanner supports your own sources for reaction rules and building blocks. So there's a CLI to standardize your own building blocks and to extract reaction rules from your reaction data following cleaning and mapping as well. So you could wire in zinc or enamine building blocks or your own in-house reactions into the same pipeline so that planning runs against your own known chemistry. So this is obviously useful if you're using a particular reaction and you want to increase the scope. So you could define your reaction and then a product, and it would give you starting materials based off of your own specified reaction. And then in the following cell, we're going to be loading in the policy network, which is the model that tells which reaction rule should we try next for this molecule. And this is a graph neural network that embeds the target or product molecule and outputs a score for every reaction rule. And then those scores act as priors for node expansion in the following step, which is the Monte Carlo tree search algorithm. And that ensures that the planner explores high probability disconnections first. So essentially, the policy network is SynPlanner's reaction rule recommender. It's what makes the search tractable really by focusing the tree expansion on the most promising disconnections first. Then the very next thing is to configure the Monte Carlo tree search, because it's essentially the search engine that consumes those policy priors and actually builds the synthetic routes. And so if you don't tune the MCTS, you either burn compute on dead ends or miss good synthesis routes that the policy suggested. So you essentially configure the MCTS next because it's where you translate the policy's guidance into search behavior and budget and then stock criteria. So you're essentially directly controlling the runtime, the route quality, and whether you hit purchasable nodes from your building blocks database. Now, obviously, you can define your target smiles just by pasting a smile string, or you could use the 2D molecular sketcher, which is included in this notebook, to draw your molecule and then convert that into a smile string, which you can then paste into the target molecule cell. Then you're going to load the target molecule defined by the smile string, which you've either just generated or you had prior. Then you're going to initialize the tree and then simply run the retrosynthetic planner. And you will see the runtime printed, so 70 seconds, the number of nodes, how many iterations, how many nodes were visited, and the number of found routes. And then in the last cell, you can just press play and you'll be able to visualize those routes in Colab. And you will also see a route score with those. Then in the next cell, we can inspect the tree object that was created during the retrosynthetic planning. So this script helps you to understand the internal structure of the tree objects by showing which of its attributes are dictionaries and how many items are stored in those dictionaries. And that can be useful for sort of debugging or exploring the data stored within the tree. And then you can change the node or the leaf ID to the node of interest. So if you found a route that interests you, defined by a node number, you can input that node number and it will give you all of the smile strings involved in that tree pathway, in that route. And then you can show the smiles from that selected route as 2D structures in the final cell. So you can visualize those 2D structures along with their smile strings as well. And then of course you can list those smile strings and you can copy those smile strings and paste them into a database searcher like Zinc22 or others or Sigma Aldrich, and you can search them by smiles to find them and find their purchasing information. Okay, so that's everything for this video on the use of SynPlanner and covers the use of SynPlanner, which is a retrosynthetic pathway predictor assisted by Monte Carlo tree search and guided by graph neural networks.